In this video I'm going to show you how to calculate the one-way within participant or repeated measures analysis of variance. In previous ANOVA videos we've seen that it's a family of techniques for comparing several groups in terms of their means on a continuous dependent variable. In all previous videos we've looked at examples where our different groups are made up by different people. So the archetypical example of that is we might have males and females that we're comparing in terms of their means on some cognitive task, but we can also have repeated measures analyses where we measure the same people repeatedly on all of our different conditions. So we might have a case that we're going to look at today where we measure people's depression levels before some therapy, we measure them again after their therapy, and we measure them again at follow-up to see if there's if the therapy made a difference. We're measuring each participant on all of our different measures. They're not just getting assigned to one group. Now let's talk about why that's useful before we actually do it. When we do an independent groups ANOVA, we talked about the fact that one of the things that creates error or uncertainty in our analysis is because we've used different people. People are different, and because there's different people in our experimental condition to what there is in our control condition, it's difficult to know whether the differences between groups are due to the fact that the groups are different anyway, or whether it's because of our experimental effect. Well, if we use repeated measures at ANOVA, we use that uncertainty because it's tested. The effect is tested within the same people. So obviously we're keeping more things constant. So there should be less error. That's the theory of repeated measures at ANOVA. It has lots of problems. The main one being that a cardinal assumption of all statistical tests is that the data points are independent. The reason why it's important that they're independent is because if they're related, we don't know if any effects are because they're already related, or whether it's due to the effect of some variable we manipulated. We're in repeated measures ANOVA, what we essentially do is make a comparable assumption and say if we know these conditions are going to be related because they come from the same people, then we can estimate how much they're related, and as long as they're related by the same amount in each condition, we can still make conclusions based on it. I'm not going to talk in any more detail about that problem in this video. I'm going to do follow-up videos on that, but let's go ahead and do the analysis. So this is the example data we've got in this video, and you see it's pretty different to what we've looked at in the past. So each participant has been tested before treatment, after treatment at a six month follow-up, and you see we've got a participant number. So participant 1's got a before treatment and after treatment and a 6 month follow-up. Just like with the regulator between groups, the first thing you need to do is calculate the total variability to be explained within our data, and we do that using the same method as we've always done for ANOVA. So first we calculate the deviations between each score and the grand mean, which is the mean of means, or the overall mean if we lump all the scores together. So if we pull this down, we see that for the first score, the deviation from the grand mean is 3.07, and we see all the deviations there for all the scores, regardless of what person or condition they came from. But we know from previous videos that some of these scores are negative and some of them are positive, and if we added them together they'd cancel each other out, so we need to square them to get rid of that problem. So we square all our values, they're all squared values, and to get measure of the total variability we're simply going to add up all those values. So we know that 1660 0.9237 units of variability after we explaining our data. Now, what could they possibly be explained by? Well, usually when we do an independent ANOVA, we have they can be explained by our effect or error, the differences between people. But in the case of repeated measures ANOVA, it's always a bit more complicated. You might wonder why I've got different people listed here, because I just said that the whole point of a repeated measure ANOVA is that we're comparing it within the same people, so it's to reduce the error. Well, we've still the total variability in our study still encompasses the fact that overall, depending on the person, some people have done better than others. Not specifically in terms of like conditions, but just generally some people will be better than others because of factors like age, as I've put as an example here. So really that's another type of error. It's not the type of error we're actually going to use, but we need to calculate it so we can work out the values that we do need to use. So how are we going to do that? Well, first thing we do is if we're just looking at differences between people, we need to equate the people somehow. So we calculate a mean for each participant, which is just the total of all their scores divided by the number of conditions. So you can see in that fifth column, I've just calculated a mean for each one of my participants. Now we just use that mean to work out how much variability is due to the effect of different participants, and that's the same equation as we've used in previous videos for calculating our effects. So in this case, we take the mean of the participant minus the grand mean that we calculated earlier, square it, and times it by the number of entities. Now, where does 3 come from in this case? It comes from the fact that mean that we just calculated, so 73.67, is created by using those 3 scores from the 3 different conditions. So we times it by 3, and once we add up all the variability for all the participants, we get a score of to 1085.7684 units of variability are explained by differences between participants. We're not gonna address that again because it's not what we're interested in when we do a repeated measures analysis. What's the next thing? Well, we need to know how much variability is created by different experimental groupings, and we do this in exactly the same way as we do for an independent ANOVA. But if there were no difference, if the only thing that was creating differences between our groups was our experimental manipulation, then we should expect that the people in each group would have exactly the same mean, because there'd be no other reason for them to vary. So we're saying if we predict that each score has exactly the mean from the group that it's in, how much variance can we explain? So we're saying here that we're going to take the mean of the first group from the grand mean, square it, which is what we always do. Where does this times 5 come from? Well, it comes from the fact that there were 5 people in the therapy group. So if we're predicting that everyone's got the mean, we're predicting that score is going to exist 5 times, and then we're doing the same for the after group with its mean, and for the follow-up group. And again, all participants completed all conditions, so we multiply them all by 5. So now that we've got those, work out the error we're actually interested in, the error we're going to use, which is the error within each participant. And this is I've put here forgetting to practice techniques. So this is the error that's not due to different people, but that's due to things we can't explain. So even if it's within the same person, they might get different means on different tasks, not based on the tasks themselves, but just because other things change between the tasks that we haven't measured. For example, they might get more tired, they might things like this. So that's what we're going to use our measure for error. And to calculate that, we're going to do very simple. If we know our total variability, and we know that there's an effective independent variable, and also there's affected participants, we know that whatever's left over is the error within people. So that's 232.6218. And we can now calculate our F-statistic, which, if you recall from previous videos, in all forms of ANOVA, is what we use to compare to a critical value table to see if we've got a significant difference or not. Before we do that, we need to calculate degrees of freedom, because those are measures of total variability due to our effects. So we need a measure of average variability, and degrees of freedom always equals the number of scores involved in the calculation minus the fixed score. So the degrees of freedom for our effect is, remember, we only use the group mean. So degrees of freedom for our effect is the number of group means minus 1. So in this case it's 2. Now, what of the degrees of freedom for our error? You can see that it's 8. Well, where does that come from? Normally, in an independent ANOVA, we take all the scores, which is 15 in this case, because everyone can produce error. Take away the degrees of freedom we've already used, so 2 in this case. But where's this 5 come from? What other scores are fixed? What other scores have we previously used in the analysis that can't change? Well, unlike in an independent ANOVA, we've calculated a separate measure of the variability within participants, and as you recall, that required us to estimate means for each participant. So for every mean we've estimated, we lose a degree of freedom as well. Now that we have those degrees of freedom, we can calculate the average sum of variability for our effect, which is the effect that we previously calculated divided by its degrees of freedom, and also the average variability accounted for by error, which is 29.0777. And what we use to assess significance is an F-statistic. So, as we've previously seen, the F-statistic is the mean square for our effect divided by the mean square for error. We'll just calculated those two. So for this for these data, this statistic is 5.89, and we can compare that to a critical value table for the F statistic with 1 and 8 degrees of freedom, and we find a probability value of 0.027, which that's less than 0.05. So we can say by conventional standards we've got a significant difference, and the therapy made some difference to our depression scores. We can't tell from this whether the before and after groups are different, or whether the before and follow groups are different, but we can say that there's some difference somewhere between our scores. So that was how to calculate the repeated measure. I hope you enjoyed.